Hi, welcome back. So in the previous video, we basically cover all the differentiation rules that you need to know for SACE mathematical methods. So now we will move on to the applications of differentiation. So of course the first application is to find the tangent or the normal on the curve. So this is not that difficult. Basically what you need to do is to find your first derivative. So if you want to find so let's say this is your curve, and then this is the point that you want to find the tangent with. So I also draw the normal. So let's say this is y equals to fx. So in order for you to identify the tangent, the first step that you need to do is to find your first derivative, which is your f prime x, at point x equals to a, for instance. So let's say this is a f of a, right? So first you need to find your f prime, and then you just, so in this case you can find the differentiation, the first derivative, and then substitute the value of x inside. So once you find that, that will be your gradient. So then you just use y minus f of a divided by x minus a equals to f prime of a. So you just use the equation of a line to identify your equation of tangent. So if you want to find the normal, you just add one step. So the first one, of course, is still identifying your f prime a at x equals to a. Second one, use m1 f prime a multiply with the gradient of the normal equals to -1 to identify your gradient of the tangent, which is minus the reciprocal of f prime a. So then the third step is still the same. Use the equation of a line to find your equation of normal. So that's how you identify the equation of tangent and equation of normal. So this is not as difficult, which is why I will just briefly go through this. So the next application is more important. That is to describe the shape of a graph. So first of all, we need the concepts of increasing and decreasing function. So increasing or decreasing function. Okay, perhaps I will just draw it diagrammatically. So what is an increasing function? You don't really need to know the proper definition for increasing function. There is a proper definition, but usually for the exam purposes, what you need to really understand is how it is going to relate between your sign diagrams and your dy/dx, and then the graph of dy/dx, for instance. So as long as you see the graph going towards this direction, so this is an increasing function. So similarly, we can sort of like roughly describe what is a decreasing function. If you see your graph going downwards, so that will be your decreasing function. So for increasing function, your first derivative has to be positive. Usually people doesn't really include 0. As a matter of fact, if you include 0 or not, it doesn't matter. So for decreasing function, it will be smaller than 0 for the first derivative. The second set of definition is that you need to know what is the idea of concave. Okay, so there are a few names for it. So you can either call it an concave, upward, or just convex function. So for here, your graph needs to be looks like this. So the property for concave upward or convex function is that your second derivative has to be greater than 0. So you also have concave, downward, or concave function. So the shape of graph will look like this. So this is given by your f double prime of x smaller or equals to 0. So then next step is to identify points. So these are functions. I need to draw a longer I might as well zoom out for a bit. So here I just briefly summarizes what are the different things that you need to understand. So roughly you have this many classes, and let's just draw it properly. Okay. So now let's look at points. So first of all, you will have stationary point. So for this particular stationary point, I will mention that this is a maximum point. So if you look at um, stationary point, which is maximum, the definition of stationary means that your f prime x is equals to 0. So if it is maximum, then it means that your point sits somewhere around here of your curve, right? So then it will mean that your f double prime of x has to be smaller than 0. So that is the definition of stationary point, which is maximum. So whenever you get this particular point, remember that your stationary point would sit at the maximum of concave downward function. So you will get this set of conditions. So if you have stationary point, which is a minimum, so then your minimum point has to be sitting at a concave upward function. So it means that your f prime x equals to 0 and your f double prime has to be greater than 0. You have a third class of stationary point, which is called the point of inflection. So these are the points where it sits in between the changes of concave function and the convex function. It's either like this or like this. So if you see this kind of shape of graph, definitely there is a stationary point of inflection. When it is stationary, it means that the gradient at that particular point, you need to show that there is a straight line. So it means that your f prime x equals to 0, your f double prime of x also equals to 0. So those are the stationary points. So the last point that you have is what we call as the non-stationary point of inflection. So when it is non-stationary, it means that your f prime is not equal to 0, but your f double prime is equals to 0. So you see this when your point sits at, again, the same thing between the convex and the concave functions, but this time when you try to draw the tangent, it is not a line parallel to your x-axis, but there is some gradient. So this is what you need to show in the exams when you are being asked these kind of things. So roughly speaking, I sort of describe all the terminologies with diagrams and their conditions. So okay, what happens if you want to find stationary point? And in other words, what are stationary point? Stationary point is you can think of it as the marks, the changes from increasing. Okay, let me define it properly. So stationary point which is, perhaps I should define it properly. Let's look at maximum point first. So maximum point marks the change from increasing function to decreasing function. So similarly, you can also define your minimum point. Is a point that marks the change from decreasing to increasing function. So on the other hand, point of inflection, whether or not they are stationary or not, it marks the change from concave upward. It can also be a concave downward. Okay, I will use the word vice versa. Marks a change from concave outward to concave downward functions, and vice versa. Vice versa means it's either concave upward to concave downward or concave downward to concave upward. So if you check back the diagram that I draw, so this portion of the graph, the left side is basically concave downward, the right side will be concave upward. Whereas the other one that I draw, the left side is concave upward, the right side is concave downward. Similarly over here. So the idea of stationary point is not necessarily marking the change from increasing to decreasing function. As you can see on the stationary point of inflection, the function as a whole is still increasing or decreasing. So the name of stationary means that your f prime x equals to 0, which is why just now I specified that it has to be either a maximum point or a minimum point. Whereas when you have a point of inflection, it always marks the changes from a concave upward to a concave downward function and vice versa. So these are the three properties that you need to know, and you can sort of like deduce it from the diagrams that I draw. So then if you want to find stationary point, you just need to find f prime x equals to 0. If you want to find inflection point, you need to find f double prime x equals to 0. Okay, so these are the key points for you to identify all the features of a graph. So if you want to find stationary point of inflection, you need to satisfy number 4 and 5. If the point itself is a non-stationary point of inflection, you only need to satisfy equation the point number 5, so on and so forth. So As I also show here, for a maximum point, your f double prime x is smaller than 0. This is also what we call as the second derivative test. So probably I should put it here. So second derivative test. So what the second derivative test tells you is that if it is a maximum point, your f prime, first thing you need to do is to make sure your f prime x equals to 0. Second thing, f double prime has to be smaller than 0, as I was written here. If it is a minimum, you still have f prime equals to 0. F double prime will be greater than 0. You cannot test point of inflection using your second derivative test. Okay, let me rephrase. For second derivative test, if it is a point of inflection, your f double prime has to be equal to 0. Technically speaking, we don't use second derivative tests to test for point of inflection, but this is the definition of point of inflection. When we use second derivative test, usually we are checking either it is a maximum or a minimum. So now let's move on to the next test, the idea of sign diagrams. So for sign diagram, you have two. One is to look at f prime. The other will be looking at the f double prime. You can also draw the sign diagram for f of x, but usually that is not as particularly useful. So for sign diagram of f prime x, the first thing that you need to identify is x when f prime of a is 0. So identify the value of a. Second thing that you need to do is to identify all the vertical asymptotes of fx. So once you identify these two, then you can draw your number line. So when you draw your number line, make sure you label what kind of sign diagram this is. And then for instance, if you have zeros over here, let's say this is A, this is B. Okay, let's say this is 0, then you just label like this. Let's say you have a vertical asymptote here, then you draw a dotted line. So for instance, the vertical asymptotes of fx, I write it as x equals to b. So that will be your vertical asymptotes. So you draw it like that. So after you draw this particular sign diagram, you need to identify all the regions. What are the signs? So substitute relevant values in each region to find out the sign. So the values are not important, but the signs are important. For instance, if a equals to 1, I can substitute f prime of 0 to find out the sign. And then I've substituted f prime 2 to find out the sign. Let's say b is 4. Then I can substitute f prime 5 to find out the sign. Okay? So the sign are important, not the value. And remember, your vertical asymptote always has to be respected. So now, let's go back to the properties. Just now I mentioned that maximum point marks the change from increasing to decreasing function. So if you have this particular sign diagram, positive, negative. So positive means increasing, negative means decreasing. So this is a typical sign diagram for a maximum point. Whereas for a minimum point, it marks the changes from decreasing to increasing function. So this will be decreasing and then increasing. So this is a minimum point. For the sign diagram of f prime x for the point of inflection, I already mentioned that point of inflection does not look at your increasing or decreasing function. It marks the change of concave upward to concave downward and vice versa. So it's either left or right increasing or left or right decreasing and so on. So for point of inflection, you can either have plus plus or minus minus. So just now I mentioned that you need to label and identify all the x equals to a when your f prime of a equals to 0. So when I do this particular labeling, this kind of sign diagram will be the sign diagram for stationary point of inflection. If it is non-stationary, you wouldn't need to mark the point at all. So this is a thing that you need to understand. So that is for the sign diagram of f prime x. So now let's look at the sign diagram of f double prime x. So following the same step, the first you need to identify your x when f double prime of a equals to 0. Identify vertical asymptotes. So this time, what you're going to do is to draw the sign diagram for f double prime of x. So let's say this is A, let's say this is B. So same thing before, here you identify, for instance, A equals to 1, B equals to 4. Yeah. Here you identify the value of f0 for instance, label down the sign, and then here you identify f2 for instance, label out the sign, and then here you identify f double prime of 5 for instance, and label down the signs. So I will just copy this particular sentence again. And that's what you need to do. So this is the only test for your point of inflection. So just now I mentioned that for point of inflection, it tells you when your function is concave upward to concave downward. So you definitely will see either of these. So if you see this kind of signs, it means this is a point of inflection. It doesn't tell you whether or not this is a stationary point of inflection. You need to combine with this particular sign diagram. So let's look at one particular examples. I probably need to think for a bit. Okay, I will pause the video for a bit, and then I continue back with the example. So I need to just think a little bit how to illustrate all the possible points inside these two sign diagram. Okay, if I do it correctly, the video should continue. So this is the example that I came up with. So let's look at this one by one. So I will do it in blue. So first of all, you are given two sign diagrams. One is the f prime, another one is f double prime. So you need to combine the information of these two sign diagrams to actually tell you what are the natures of all those points. So let's look at this one by one. So over here, when you look at the f prime of the sign diagram, plus means increasing function, minus means decreasing function. So over here, you can already see that A has to be maximum. So then the second one, between A and B, you have minus, and then between B and your vertical asymptote, you have plus. So this B has to be a minimum. So in fact, if you go to your f double prime, just now I mentioned that for your maximum point, your f double prime has to be smaller than 0, which is why it lands on the negative region for your f double prime. Whereas for B, the f double prime has to be greater than 0, which is why when you look at your f double prime, B falls into the positive region. So that is also another test for you to double check your answer in this case. So then you shouldn't read your sign diagram across your vertical asymptotes. So this region is basically off limits. You don't need to read that. So now let's look at C. C, both are positive, so it might be a stationary point of inflection. In fact, when you look down, there is a change in sign in your f double prime. from minus to plus, and your f prime is the same sign. So this is a stationary inflection. So your point D plus then minus. I might have messed up with the sign. Plus minus should be minus, so this should be plus. Sorry about that. So double check. This should be a maximum point, and it corresponds to the negative region of your f double prime. So that's how you identify all those points. There is one more point here, E, that does not correlate to any of your zeros at your f prime of your sign diagram. So this is a non-stationary inflection. So that's how you read your sign diagram based on the given f prime and f double prime.